Hello everyone, welcome back to this week's algebraic graph theory seminar. This week, Xiaoye Liang, she's going to talk about thin distance regular graphs that are Grassmann graphs.
Okay, thank you for your introduction, and thank you to the organizers for giving me a chance to take this talk. But I have to apologize for my poor English, sorry. And in this talk, I use some simple words, and I hope you can understand me. Okay, the topic is thin distance regular graphs with classical parameters are the Grassmann graphs. And this work joint with Professor Koolen and Ying-Ying. Okay, there are three parts. I'll first give introduction and show you our results, and if I have enough time, I'll show you the sketch of the proof. Okay, let's see some definitions and notations. Let gamma be a graph that's finite, simple, undirected, connected. And here I use X denotes the vertex set, and I denote the edge set. And any two vertices x, y are adjacent if x, y in R. We define distance between any two vertices x and y is to be the length of a shortest path connecting x and y, and denoted by partial xy. A diameter of a graph is a maximum distance for all pairs of vertices. Now I use gamma Rx to denote the set of vertices whose distance from X is I. And a graph is called regular with valency K if the cardinality of gamma 1x is K for all vertices in gamma. Then we can see distance regular graphs. A graph gamma is called distance regular if there are constants AR, BR, CR such that for any two vertices x, y at distance I, then we have AR, BR, CR is this. We can see this picture. Here we have x, y at distance I, and the all neighbors of y lie in these three cells. Gamma r minus 1 x, gamma rx, and gamma r plus 1x. And the number of neighbors are CR, AR, and BR respectively. Then we can see gamma is regular with valency B0 denoted by K. And AR plus BR plus CR is exactly K for all I. Then we see AR can be determined by K and can be determined by B0, BR, and CR. So we define all of BR and CR intersection area. And these are important parameters for distance regular graph. And there are some distance regular graphs. The intersection area can be determined by another 4 parameters. We call that classical parameter dB alpha beta. Here, d is the diameter of the distance regular graphs, and the intersection error can be determined by these 4 classical parameters according to these 2 formulas. So we have know the parameters of the most of distance regular graphs with the diameter at least 3. With the classical parameters are uniquely determined by the intersection error. For the distance regular graph, we usually see the diameter at least 3, because when diameter exactly 2, that's a strongly regular graph, and there are much study on that. So we usually separate them. Okay, okay, so if we want to do something on distance regular graph by the intersection error, we usually sometimes we use classical parameters. Okay, then we can see some examples. So here is Hamming graphs. Hamming graph. Okay, the definition is we give a q set, and the vertex of Hamming graph is this, and x, y are adjacent if they differ exactly 1 position. So Hamming graph is a distance regular graph. The intersection errors here, and it has classical parameters. And another example is Johnson graphs. We still have n set, and a vertex of Johnson graph is d subset of omega, and any 2 vertices x, y are adjacent if the cardinality of x join y is exactly d minus 1. So here are the special Johnson graphs. So for Johnson graph, we have this one. JND is isomorphic to JN n minus d. So diameter is minimum d and d minus 1. So with loss of generality, we usually assume that d n greater than and equals to d. The Johnson graphs is also distance regular graph. We know their intersection error and the classical parameters. Then we can see Grassmann graphs. It's actually Q analog of Johnson graphs, and it's also our research object. Okay, we for define this, we have this omega. Omega is n dimension vector space over FQ. That's a finite field. And the vertex of the Grassmann graph is d-dimension subspace of omega. And x and y are adjacent if the dimension of x joining y is exactly d minus 1. So same as Johnson graphs, we also usually assume that n greater than and equals to d. And we still know the intersection error and the classical parameters for Grassmann graphs. So for a distance regular graph, we can we know its intersection error. One is interested whether there exists a unique distance regular graph with a given intersection error. For example, Peterson graph is determined by its intersection error, and the Hamming graph is determined by its intersection error, unless Q is 4 and D greater than or equal to. In this case, we call the dupe graphs. The Johnson graph is determined by its intersection error unless ND equals 8 and 2, in which case they call the Chang graphs. So how about Grassmann graphs? In 1995, Match showed that Grassmann graph is characterized by their intersection error, except for these cases. N equals 2D or N equals 2D plus 1 when Q greater than or equals 2. And N equals 2D plus 2 and Q is 2 or 3. The N is 2D plus 3, Q is 2. And in 2018, the Xiaoye and Koolen solved this case. N equals 2D and Q greater than or equals 2 with large enough diameter. So we want to solve the left cases. For N equals 2D plus 1, in 25, Van and Koolen discovered twisted Grassmann graph that have the same intersection error as the Grassmann graph with N equals 2D plus 1. So from this, we know not all of the Grassmann graph can be determined by its intersection error. And the twisted Grassmann graph is a difficult case. So we want to skip this difficult thing. So we solve Grassmann graph at a condition they are seen. Because twisted Grassmann graph is not seen. I will introduce the concept of sin later. So this we want to do. We showed the Grassmann graphs with N between 2D plus 1 and 2D plus 3 for all Q greater than or equals 2. This includes all left cases. We show this Grassmann graph with large enough diameter is characterized by their intersection error. Okay, let's introduce what's the thing. This is related to Taylor algebra. So here I show you the Taylor algebra. We let gamma be a distance regular graph with diameter d, and A be is adjacency matrix. So adjacency matrix, the xy entry is 1 if x adjacent to y, 0 otherwise. And for this graph, if we fix base point x, we can partition its vertex sets into d plus 1, cells, that's gamma x and I from 0 to D. Then we can define a diagonal matrices ER star with respect to X. This is about best point. The Y entry of ER star is 1 if Y in gamma X, 0 otherwise. For example, the ER star looks like this, and here is gamma Rx. Okay, then this matrices A and all of ER star is generated algebra. We call it Tablic algebra with respect to X, and denoted by T. And for the graph, we also can define V. V is a subspace that's equipped with the Hermitian inner product. So V is Cx is actually spanned by vectors. Here x hat is this vector. Only 1 in X position. So we see the Tablic algebra can X on V. And we call a subset of V T module if for all elements in Tablic algebra and all elements in W. The TW still in W. T small w is still in capital W. We call W is T module. And the W is called irreducible if it's non-zero and contains no T submodule besides 0 and itself. So for an irreducible T module, we can define some concepts on it. Firstly, we give a ordering of ER star. Usually, we just use E. Gives ordering is E0 star, E1 star, and ET star. Here's the ordering related to the distance. Okay. We define endpoint of W is minimum R such that ER star W is non-zero. And the diameter is the number of non-zero ER star W minus 1. So we can see this picture. Here we can decompose the V into D plus 1 parts. And we here have a irreducible T module W. Here we see this one. One is the minimum R such that ERW is non-zero. So for this irreducible T module W, the endpoint is 1. And for a distance regular graph, if I have a non-zero vector here, and we use Tablic algebra X on this, it can go continuously. And here for this example, we can see the diameter is D minus 1. D minus 1, the diameter. And W is seen if the diameter ER star W at most 1 for all I. So this one, if EI star W is non-zero, then dimension is 1. Is 1. So this thin module, thin irreducibility module. Now graph gamma is called I thin if for each irreducible Tx module of endpoint at most I is thin for all x. And gamma is thin if it's I thin for all I. So now we see what's a thin distance graph. Okay, then we can see our results. We showed this. Let gamma be a thin distance regular graph with classical parameters. These classical parameters. That's is same as the classical parameters as the Grassmann graph. And if d greater than and equals q defined as this, then gamma is the Grassmann graphs. So actually thin condition thin is stronger. So we can weak this. We show if gamma is a one thing, and add mu graph regular condition inside, then we can get the same result. Here, what's the mu graph regular? That's a regular graph, and each subgraph induced on gamma 1x and gamma 1y for any two vertices x, y at distance 2 is regular with valency L. If this theorem holds, and then we replace the one thing condition by thing, we can get the corollary by this theorem. Because if gamma is a thin distance regular graph with classical parameters and the diameter at least 5, then gamma is mu graph regular. So if this one changed by thin, we can delete this condition. So this theorem is our main theorem. We will show this one. So how to prove this? The technique is partial linear space. A partial linear space is an incidence structure, PLI, where P is the point set, L is a line set, and I is the incidence relation between P cross L, such that every line is incident with at least 2 points, and any two distinct points lie on at most one line. And the point graph of a partial linear space is a graph defined with the P as its vertex set, and the 2 points are adjacent if they are collinear. So for to prove our main result, we use the BCN's theorem 9.3.9. This theorem shows that if we have a partial linear space satisfy these 5 conditions, then this partial linear space is isomorphic to this one. In particular, the point graph of this one. It's exactly just a Grassmann graph. So we want to construct a partial linear space satisfy these conditions. Then we can show the point graph. The point graph gamma is a Grassmann graph. So we want to construct a partial linear space. But how to do that? For Grassmann graph, we know some results. Firstly, we define local graph. Local graph at a vertex x of a graph gamma is a subgraph induced on gamma 1x. And for distance regular graph, if gamma is distance regular graph, and the local graph are same for local graph are isomorphic for all x. And we know the local graph of a Grassmann graph is isomorphic to this one, q-click extension of this grid. And we also know the spectrum of the q-click extension of the grid. So we know the spectrum of local graph of the Grassmann graph. Okay, because we condition is a one thing. One thing means the irreducible T module of endpoint 0 and 1 is the same thing. And this 0, if endpoint is 0, there are unique T modules of graph, and we know it clearly. So we only consider the irreducible T module of endpoint 1, and this one related to the local graph. So we want to research on the local graph. And because the local graph of Grassmann graph is isomorphic to this one, so we research on something on this. Okay, if we do something on local graph, we need more definitions. Edge regular and co-edge regular. That's a regular graph with parameters VKA. Here V is vertices number, and the K is valency, and the M is the common numbers for any two adjacent vertices. And a regular graph is called co-edge regular with parameter VKC. If for any two distinct non-adjacent vertices have exactly C common neighbors. And this lemma shows us the relation among edge regular, mu graph regular, and the co-edge regular. Let's see it. If gamma PR graph that's edge regular with parameters VKA and mu graph regular with parameter AL, then any local graph of gamma is co-edge regular with parameter KAL. So this L is an important parameter for us. Then we can show something on q-click extension of the grid. Here we let G be a graph that's conspectral with the q-click extension of the grid. Conspectral means these two graphs have same spectrum. Then we get these three results. That's helpful to construct a partial linear space. Okay, the main thing is this one. We define a grid click if it contains at least this number vertices. This number is nearly half k. And if T2, the first grid T2 at is greater than this number, then we can see any vertex of G lying a unique grid click. And from these three results, we can prove our main result. Main result. Okay. So here gamma is a one thin distance regular graph with these classical parameters, and we assume D greater than Q. We assume first gamma is mu graph regular, then we can show this local graph of gamma is co-edge regular. It's co-edge regular because distance regular graph is edge regular. And if we set T is this, T1 is this, T2 is this, we can see the local graph is a conspectrum with a q-click extension of T1 times T2 grid. And we show there exists a click contains this vertices, and here 1 is a base point, and this QT1 in the local graph of X. Okay, yes. So we can use our three results on it, and finally show the local graph exactly exactly the q-click extension of the grid. Then we can define a line if it contains at least this number of vertices, and let this L be the set consisting of all lines. Then show this one. This one is a partial linear space such that gamma is point graph. Here X is the vertex set of Grassmann graph. L is this line. So finally, we construct this partial linear space and can show the point graph gamma is a Grassmann graph according to this theorem. Okay, that's all. Thank you for your attention.
Thank you for the talk.
Thank you.
So, is there any question for Xiaoye?
I have a question.
Yeah.
So your results require some bounds on the diameter. Oh,
we need diameter large enough.
Right. So why do you have to make that assumption? What goes wrong if the diameter is too small?
Actually, if diameter is small, the situation is complicated. So it may be difficult to classify them. So usually we consider the diameter is large enough. Yeah. So we don't know about diameter is small. Yeah, we haven't considered it.
Well, when you say it's complicated, what are you thinking of, a certain formula? Or what situation are you thinking of that's so complicated?
We didn't consider that, but usually for distance regular graph, for example, a polygon, if the diameter is small and there are many situations. So for because if we want to classify the actually the same q-polynomial distance regular, we consider diameter large enough. Yeah. Yeah.
Okay.
Okay, so is there any other question for Xiaoye?
Well, I have another question.
Okay.
Yeah.
Go ahead.
So you're looking at in the slide right there, the second to the last line, the points and lines are the points are the vertex set for the actual Q Johnson graph.
Yes.
And then you're looking at the next one up. What if you go down instead of up? You look at your line. What if you look at the situation where your lines become the vertex set for the Grassmann graph?
So I'm sorry, can you repeat it?
Oh, okay, right. Yeah, in this slide right here. Suppose you replaced D plus 1 by D minus 1.
You mean here? Here?
Yeah, right there. Yeah. So then again, you would get a kind of point line system, but the details would be somewhat different.
Oh, this may, but I haven't think about that.
Okay, I was just curious.
Yeah, maybe we can. Yeah, we need to think. Yeah, think this.
Okay, I was just curious. Yeah, good.
Oh, thank you.
Okay, so any other questions?
Well, question.
Yeah.
Well, do you think you will be able to remove the bounds on the diameter with more
diameter?
work? Yeah.
Okay. You mean this, you mean here the diameter? Yeah.
So you have this assumption, D at least chi of Q.
Yeah.
Okay, now maybe you with some more work, maybe you can remove that assumption.
Because we want to use this theorem, and we want to use mu graph regular, and here we need diameter at least of yes, we okay, let's see. Where? Okay, here. here this result. It because we show this one needs this condition, and this condition may can determine the D greater than KQ. So we define KQ from here.
I see.
Yeah.
Okay, got it. Very nice.
Yeah.